My name is Harriet, and my project is on the effect of urban heat island mitigation strategy on surface and atmospheric temperature. Urban heat islands, or UHIs, refer to cities that are consistently warmer than their rural counterparts. This occurs because man-made surfaces re-emit more of the sun's heat than natural surfaces. As a result, cities are 0.5 to 4 degrees warmer than nearby rural areas. This small increase in temperature has significant implications. UHIs intensify global warming and contribute to heat waves and heat-related deaths, which are already the #1 cause of weather-related death in the US. Additionally, one model estimates that the total economic cost of climate change could be 2.6 times higher when UHIs are considered than when not. Luckily, several strategies exist to combat UHIs, including green roofs, cool pavements, and trees. Green roofs are vegetation planted over a roof that reduce UHIs through physical shade and evapotranspiration. Tree canopies, which are represented by moss in this experiment, combat UHIs in a similar way. Cool roofs and cool pavements are those made with high albedo materials that reduce UHIs by reflecting heat from the sun. This experiment aimed to use simulations to determine which of these mitigation methods is most effective in reducing UHIs. The independent variable was the mitigation measure, with the experimental groups being the aforementioned strategies and the control being no mitigation measure. The dependent variables were the increase in air and surface temperatures. It was hypothesized that the cool roofs would be most effective in preventing heat gain due to their high solar reflectance and greater surface area. To conduct the experiment, models were constructed out of plywood to represent 4 city blocks and the intersection between them. The roofs and base were painted black as the control, and the mitigation strategies could be applied one at a time. The temperatures in the air above the simulation and at the surface of the base and the roofs were measured. A heat lamp was then turned on for 1 hour, after which the temperatures at the same 3 spots were measured again. This process is repeated 10 times for each mitigation strategy, and the increases in temperature were calculated, averaged, and organized into a bar graph. The control had the highest mean at all 3 spots, while the cool roofs had the lowest mean for the air and roof temperature, and the trees had the lowest mean for the ground temperature. ANOVA test yielded p-values less than 0.05, suggesting the data was statistically significant and allowing the null hypothesis to be rejected. Additional t-tests were run to further understand the significance of the data, which showed that all differences were statistically significant except for between groups with very similar means. All 4 mitigation measures produced lower means than the control. The hypothesis was generally supported as both the cool and green roofs allowed for the least increase in air temperature, with no statistical significance between the two. A reason for the superior performance of the roofs in this experiment could have simply been due to their greater surface area. The roofs comprised 56% of the total surface area of the simulations, while the cool pavements and trees comprised 44%. However, the ratio of ground to roof used was very purposeful, as an analysis of diverse cities found that pavement covers around 30 to 45% of land in cities. For the ground temperature, the green and cool roofs were less effective because they did not directly affect the ground, while the tree canopies were most effective, followed by the cool pavements. Cool pavements combat UHIs by reflecting heat, while trees prevent as much heat from reaching the pavement in the first place. This experiment suggests that the physical shade provided by trees is more effective at cooling a surface than the solar reflectance provided by cool pavements. Similarly, for the roof temperature, the cool pavements and trees did not yield any significant difference compared to the control because they did not directly affect the roofs, while the green and cool roofs were much more effective. These results are conducive with other studies, as both have been shown to decrease roof temperatures by 28 to 40 degrees. While the data collected is still insightful, it is important to understand its limitations. The moss suspended over the simulation in the experiment may have provided denser shade than actual trees, which could have skewed the results. Similarly, it is hard to predict how well the small scale of the experiment translates to a real city. The use of larger simulations or the comparison of real cities where these strategies have already been implemented could address these concerns in the future. Also, every city is geographically diverse, and it is unrealistic to assume, for example, that pavements make up exactly 44% of land in all cities. As such, a similar experiment that eliminates all geographical variables could yield results that are more easily applicable to a variety of cities. In conclusion, this experiment supports the effectiveness of all 4 mitigation strategies examined and suggests that cool and green roofs are the most effective in decreasing urban temperatures. UHIs are becoming increasingly relevant as global warming and heat waves increase and intensify. Given this, it is vital to continue to research and compare mitigation measures, as was done in this experiment. Thank you for listening.